Hello students, welcome to RD Chemistry. In this video, I'll discuss activation energy of the forward reaction, backward reaction in endothermic and exothermic reaction. So let's start now. So let me start with energy profile diagram of exothermic reaction. And here is the diagram. Let me draw the y-axis and the x-axis. Along the y-axis, the potential energy of the reactant and the products. On the x-axis, let me have the reaction coordinate. Reaction coordinate is also known as the progress of the reaction. Assume you have got initially the energy of the reactant. This is not enough. They have to have more energy to form the activated complex. Then activated complex decomposes to give the products. Assume this is the energy of the products. And this is the formation of the activated complex. Okay, this is known as the activated complex. Energy of the activated complex. Right? Now see here, this is the energy of the reactant and this is the energy of the products. And this difference is known as the delta H enthalpy of the reaction. Remember, enthalpy of the reaction. Generally, enthalpy of the reaction is equal to enthalpy of the products minus enthalpy of the reactant. In the exothermic reaction, if you see properly, energy of the product is actually less compared to that of the reactant. Correct? The energy of the reactant, the energy of the product. So therefore, energy of the reactant is more, there should be a negative quantity. Right? Now, this difference you can see here from the reactant energy to the energy of the activated complex. This is the activation energy required. And this is for the forward reaction. See carefully. In the backward reaction, product become the reactant. Therefore, this difference, this is called the energy of activation for the backward reaction. Okay, and see here, from 0 to the energy of the activated complex, the entire term is called the threshold energy, ET, threshold energy. Remember the terms: threshold energy, activation energy, forward reaction, backward reaction, enthalpy of the reaction, delta H. Okay, fine. Now see in this graph, energy of the activation in the backward reaction is greater compared to energy of activation in the forward reaction. So the graph. Okay, now I'll write down for the forward reaction. Okay, for the forward reaction. If I write the forward reaction, I can write, see carefully, ET is equal to, I will connect energy of activation in the forward reaction plus the energy of the reactant, the length. See here, okay? This length, or you can see here, I'll darken it. This length plus this length, okay, is equal to energy of activation. Threshold energy is equal to energy of activation for the forward reaction plus the energy of the reactant. Therefore, energy of activation in the forward reaction is equal to ET minus R. Okay. If I do the same thing for the backward reaction involving the energy of activation for the backward reaction. So you go for backward reaction. So we go for backward reaction. If I go for backward reaction, see carefully, the entire length threshold energy I will connect to the energy of activation of the backward reaction. Can you see here? This length. And I can add this extra length. This is the energy of the product, correct? This is the energy of the product. Therefore, I can write down activation energy in the backward reaction is equal to the threshold energy minus the energy of the product for the backward reaction involving energy activation backward reaction. Okay. Now, how to find out delta H in general other than enthalpy for the product and the reactant? So energy of activation the forward reaction, always remember, minus energy of activation the backward reaction. Now if you see carefully here, the length, okay, the length of the activation of the forward and backward. Now see carefully, backward reaction energy is more, the length is more, correct? So I'll get a negative quantity. Remember, for exothermic reaction, delta H is a negative. Also you can see here in terms of enthalpy for the product and enthalpy for the reactant, this one, this is also negative, right? Let's see energy profile diagram of endothermic reaction. It will be the similar graph. Okay. So this is the energy of the potential energy of the reactants and the products. Here is the reaction coordinate. Reaction coordinate. Okay. Assume this is the energy of the reactant. They will become the acted complex and they will form the product. Okay. Right, and this is the energy of the product. Now see the difference, this difference, this is known as the enthalpy of the reaction. Okay, now if I go for, now this is the energy of activation in the forward reaction, this is the energy of activation in the backward reaction. Remember, for endothermic reaction, energy of the product is more compared to energy of the reactant. That means delta H is equal to enthalpy of the product minus enthalpy of the reactant. Enthalpy is nothing but energy. So product energy is more, therefore it is a positive quantity. Also remember, for endothermic reaction, energy of activation in the forward reaction is greater compared to energy of activation in the backward reaction. For the reverse to that of the exothermic reaction. Okay, so we'll solve some problems on this. Read this question. For a given reaction A giving B, energy of forward and backward reactions are 19 and 9 kilojoules respectively. Potential energy of A is 12 kilojoules per mole. Calculate enthalpy of the reaction delta H, threshold energy ET, and the potential energy of the product you have to calculate. Okay, now see here, energy of activation forward backward is given. For the backward reaction, the value is less. That means it is an endothermic reaction. Suppose I have to plot the graph. Let me plot the graph. Say this is the energy of the reactant here. Okay, for endothermic reaction I should have like this graph. This is the energy of the product, that is B here, and this length is equal to delta H, correct? They're asking for what is the energy of the product B. They're asking for what is the energy of the product. What is the energy of the product we want? Energy of the reactant has been given, that is equal to 12 kilojoules per mole. Also you have to calculate the threshold energy, this entire length. This entire length is the ET, how much it will be. And they're given for the forward reaction activation energy, that is this length is given, energy of the reactant to the acted complex. This has been given, this is equal to 19. And for the backward reaction they are given, backward reaction means this is the one. They are given, it is equal to 9 kilojoules. Correct? How do you calculate the enthalpy reaction? Enthalpy reaction is equal to energy of activation in the forward reaction minus energy of activation in the backward reaction. Correct? So forward it is equal to 19 minus backward is equal to 9 is equal to 10 kilojoule per mole, correct? Kilojoule per mole. And this is a positive quantity, so it is an endothermic reaction. Correct? Now we'll calculate threshold energy. Now how to calculate threshold energy? See the graph properly. The entire threshold energy ET length is equal to, so that is a 19 plus 12 it becomes, correct? Therefore energy of activation energy in the forward reaction plus that of the energy of the reactant. Got it? 19 plus 12. So that too is equal to 31 kilojoules per mole, correct? So enthalpy of reaction is done, threshold energy reaction is done, and potential energy you have to calculate. How to calculate the potential energy? Now if you see carefully, I can also write a threshold energy is equal to this 9 plus energy of the product, right? That is 9 plus energy of the product B. Threshold energy we already have calculated, that is equal to 31 is equal to 9 plus energy of the product B, which is equal to energy of the product B is equal to, it is a 31 minus 9, which is equal to 22 kilojoules per mole, right? So we'll have to identify whether it is an endothermic reaction or exothermic reaction. Hope it is clear. See the next question. For a given reaction taking place 3 steps, rate constant K1, K2, K3, the overall rate constant for the reaction is K is equal to K1 into K2 divided by K3 they are given. And activation energy for the 3 steps, 1 to 3 stages are respectively 40, 50, 60 kilojoules per mole. What the activation energy for the overall reaction? We will have to calculate. I'll use small trick here. We'll not go for the lengthy method. I want to calculate the energy of activation for the overall reaction. So what I'll do is K1, K2, that means EA1 plus EA2. Okay, add the two values. Divided by K3 is there, so you deduct it, energy of activation energy for the third step. So it is equal to, so 40 plus 50 minus 60, which is equal to 90 minus 60 is equal to 30 kilojoules per mole. Okay, right? Easy. What if they are given K is equal to K1 into K2 divided by K3 to the power say 1 by 3 are given, assuming. Okay. In this case, how do you calculate activation of the overall reaction? So activation of the overall reaction is equal to, we will be writing 1 by 3 into energy of activation of the first one, energy of activation second step minus energy of activation third one. We already calculated EA1 plus EA2 minus EA3, that is equal to 30 divided by 1 by 3 is equal to 10 kilojoules per mole. Okay, right? Please do subscribe, share and like the video. Have a nice day.